In December 2025, 17 B-1B Lancer bombers thundered back to Ellsworth Air Force Base after a 10-month absence, transformed by war and technology. Veterans of Iraq, Afghanistan, Syria, and Venezuela, they returned carrying a chilling new role. The Air Force's $50 million External Heavy-Stores Pylon program has reimagined the aging Lancer into a hypersonic strike platform capable of unleashing dozens of long-range or hypersonic weapons in one mission. Why are military planners worldwide terrified of this development? How does carrying hypersonic missiles externally change the strategic balance? Join us as we explore how the B-1B Lancer's return with revolutionary new capabilities has changed modern air warfare. For years, the Air Force attempted to retire the entire Lancer fleet, arguing the aircraft were too expensive to maintain and redundant given the coming B-21 Raider stealth bomber. By 2023, only 45 B-1Bs remained operational from the original fleet of 100, built in the 1980s. The bombers had been working mercilessly during 2 decades of continuous combat operations in the Middle East and Afghanistan, accumulating flight hours at rates far exceeding original projections. Each flight hour required 48.4 hours of maintenance, making the Lancer one of the most maintenance-intensive aircraft in the inventory. Structural fatigue, parts obsolescence, and aging systems created constant readiness challenges that frustrated commanders and drained budgets. Congress, however, saw things differently from Air Force leadership. Lawmakers recognized that retiring the B-1B fleet before the B-21 achieved full operational capability would create a dangerous bomber gap precisely when tensions with China and Russia were escalating. The B-2 Spirit fleet numbers only 20 aircraft, far too few to cover all potential contingencies. The B-52 Stratofortress, while being modernized with new engines and radar, remains subsonic and vulnerable. Without the B-1B's unique combination of speed, payload capacity, and ability to operate in contested environments, American air power would lose critical capabilities. Congressional mandates, therefore, kept the Lancer flying, but simply maintaining the status quo wasn't enough. If these bombers were to remain relevant against adversaries deploying increasingly sophisticated air defenses, they needed revolutionary new capabilities. The solution emerged from an unexpected quarter: the Hypersonic Weapons Testing Program. The Air Force had been using B-52 bombers as test beds for hypersonic missile development. But the aging Stratofortresses were overwhelmed with modernization work, including new engines, advanced radar systems, upgraded communications gear, and countless other improvements scheduled over the next 7 years. Boeing, which acquired Rockwell's bomber division, proposed an alternative: modify B-1B Lancers to carry hypersonic weapons externally, offloading testing from the B-52, while simultaneously creating an operational capability that could rapidly enhance the bomber force. Between fiscal years 2022 and 2023, the Air Force invested $20 million developing an external carry-enabled testbed, successfully demonstrating that B-1Bs could execute captive carry of 5,000-pound class stores and release proven weapon shapes from load-adaptable modular pylons. This demonstration proved transformative because it validated a concept that would fundamentally change how B-1B fights. The Lancer was originally designed in the 1970s and 80s to penetrate Soviet airspace at low altitude and high speed, either dropping nuclear weapons or firing nuclear-tipped cruise missiles. When the nuclear mission was eliminated in 1994 under the START Treaty, external hardpoints were sealed to comply with arms control verification requirements. The aircraft could only carry weapons internally, limiting it to 24 joint direct attack munitions or similar weapons in its 3 internal bomb bays. While substantial, this payload paled compared to what the bomber could theoretically carry if external stations were reopened. The LAM pylon testing proved external carriage was feasible without compromising aircraft safety or performance, opening the door to a capability transformation that would make the B-1B the most heavily armed conventional bomber ever fielded. The fiscal year 2026 budget request formalized this transformation, allocating $50.26 million to the External Heavy-Stores Pylon program. This funding supports comprehensive development, including computational fluid dynamics modeling and wind tunnel testing of various external pylon and weapon configurations, hardware designed to modify aircraft line replaceable units and wiring, and software updates enabling the store's management system to recognize external pylon stations and weapons. The work is proceeding on an aggressive timeline because military planners recognize that China's military modernization and Russia's increasingly aggressive posture create urgency for enhanced capabilities. Initial installations will begin in fiscal year 2026, with testing and validation continuing through 2027 and beyond, ultimately equipping the entire operational B-1B fleet with external carriage capability. The weapons integration possibilities are staggering. With LAM pylons installed on external hardpoints, a single B-1B will be able to carry 36 AGM-158 joint air-to-surface standoff missiles, tripling its current capacity. The JSSM is a stealthy cruise missile with a range exceeding 570 miles when fired from altitude, capable of penetrating sophisticated air defenses and destroying high-value targets with a 1,000-pound warhead. Imagine a B-1B approaching defended airspace from standoff range, unleashing 36 JASSMs simultaneously at different targets across a wide area. Enemy air defense operators would face the nightmare scenario of tracking and engaging dozens of low-observable cruise missiles converging from multiple directions, each capable of destroying critical installations like command posts, radar sites, missile batteries, or communications facilities. The volume of fire would overwhelm defensive systems designed to engage a handful of threats, creating gaps that follow-on strikes could exploit. The AGM-158C long-range anti-ship missile integration transforms the B-1B into a naval strike platform unlike anything currently operational. LRASM was specifically designed to defeat advanced air defense systems on warships through a combination of stealth, sophisticated electronic warfare, and intelligent autonomous targeting. The missile can identify and prioritize targets independently, sharing information with other LRASMs in flight to coordinate attacks that maximize damage while minimizing exposure to defensive fire. A B-1B carrying 36 LRASMs represents a ship-killing capability that could devastate an entire enemy naval task force in a single strike. Chinese or Russian planners attempting to project naval power face the prospect of American bombers launching waves of these missiles from beyond the range of ship-based air defenses, systematically destroying high-value vessels like aircraft carriers, cruisers, and amphibious assault ships. The hypersonic weapons integration represents perhaps the most terrifying capability enhancement. The Air Force has requested funding in the 2026 budget to acquire AGM-183A air-launched rapid response weapon missiles, a hypersonic boost glide system that accelerates to over Mach 5 and maneuvers unpredictably during flight, making interception nearly impossible with current defensive technologies. When the External Heavy-Stores Pylon program reaches full maturity, a single B-1B will theoretically be able to carry 31 hypersonic missiles, combining internal and external carriage. 31 weapons, each traveling faster than a mile per second, each capable of destroying hardened targets that conventional weapons cannot touch, each essentially invulnerable to existing air defense systems. This capability alone would fundamentally shift the balance of power in any potential conflict with China or Russia. Understanding why this terrifies adversary military planners requires examining the strategic context. China has invested hundreds of billions of dollars in anti-access area denial capabilities, specifically designed to keep American forces, particularly aircraft carriers and bombers, away from areas China considers vital to its interests. The South China Sea, Taiwan Strait, and approaches to mainland China bristles with advanced air defense systems, including the HQ-9 long-range surface-to-air missile, sophisticated early warning radars, and hundreds of fighter aircraft. Chinese strategists assume that even if American bombers penetrated these defenses, they could only carry limited weapons loads, allowing Chinese forces to absorb the strikes and continue operations. A B-1B carrying 36 standoff cruise missiles or 31 hypersonic weapons shatters this assumption completely. A handful of bombers could now deliver firepower equivalent to what previously required dozens of aircraft, saturating defenses and creating devastation that Chinese forces cannot sustain. Russia also faces similar concerns in European and Arctic theaters. Russian air defenses in Kaliningrad, Crimea, and along the country's western borders are designed to create defensive bubbles protecting critical military installations and industrial centers. The S-400 and newer S-500 air defense systems can engage aircraft at ranges exceeding 200 miles and altitudes up to 100,000 feet, creating zones where conventional bombers face unacceptable risk. However, these systems have limited magazines. An S-400 battery can engage only a certain number of targets before requiring reloading, a process that takes time and exposes the system to follow-on strikes. If American B-1Bs can launch 36 cruise missiles or multiple hypersonic weapons from standoff ranges, they can overwhelm these defenses through sheer volume, exhausting interceptor magazines and creating gaps for additional strikes. The operational flexibility that external carriage provides deserves special emphasis. Traditional mission planning required careful calculation of weapons loads based on target sets, with aircraft configured for specific missions during ground operations. If the tactical situation changed during flight, bombers often couldn't adapt because they lacked the right weapons mix. External pylons change this calculus fundamentally by allowing mission flexibility previously impossible. A B-1B could carry a mix of JDAM precision bombs internally for attacking fixed installations, while simultaneously carrying externally JASSMS for destroying air defenses or LRASMS for engaging naval targets. If intelligence identifies unexpected targets during the mission, the bomber has options to prosecute them without aborting or requiring additional sorties. The Pacific theater focus drives much of this development. Pentagon strategists have identified China as the pacing threat for military planning, and potential conflict scenarios in the Indo-Pacific present unique challenges that the upgraded B-1B is specifically designed to address. The vast distances across the Pacific Ocean strain logistics and aerial refueling capacity, limiting the number of aircraft that can effectively strike targets deep inside Chinese-controlled territory. The B-1B's combination of long-range, high speed, and massive payload means fewer bombers can deliver equivalent firepower compared to tactical fighters requiring multiple refuelings and carrying limited weapons loads. The bomber can cruise at over 600 miles per hour, covering distances that would take subsonic B-52s significantly longer, compressing enemy response timelines and complicating defensive planning. The recent return of B-1Bs to Ellsworth Air Force Base after 10 months at Grand Forks highlights the integration between legacy bombers and future capabilities. The aircraft had been temporarily relocated to allow massive infrastructure construction at Ellsworth, preparing for B-21 Raider arrival in the coming years. Over 20 major facilities were constructed or renovated, including specialized hangars, maintenance facilities, weapons loaders training buildings, and upgraded runways capable of handling both the aging Lancers and future Raiders. When the B-1Bs returned in December 2025, they landed on freshly completed runways that had been closed for 11 months, marking a symbolic transition where old and new capabilities will coexist for over a decade as the bomber force transforms. This coexistence is critical because the B-21 won't achieve full operational capability until the early 2030s, and current procurement plans call for only 100 aircraft. Many analysts argue that this number is insufficient for simultaneously deterring threats in Europe, the Middle East, and the Indo-Pacific while maintaining strategic nuclear deterrence. Some experts have suggested the Air Force needs closer to 175 or even 225 B-21 Raiders to meet all requirements. Until that debate is resolved and additional aircraft are procured, the upgraded B-1B fleet must carry a substantial burden. The External Heavy-Stores Pylon program ensures these aging bombers can compete in increasingly contested environments while the service transitions to next-generation platforms. The maintenance and readiness improvements accompanying the external carriage upgrades deserve attention because they address long-standing B-1B challenges. The integrated battle station modernization, completed fleet-wide, replaced analog cockpit systems with modern digital displays, improving navigation accuracy, situational awareness, and reducing pilot workload. The BEAST program at Dyess Air Force Base accelerated modernization timelines by years, incorporating Link 16 tactical data links enabling real-time information sharing with other aircraft and command centers, secure communications resistant to jamming and interception, advanced defensive avionics that can detect and counter threats more effectively, and increased data storage, allowing the bomber to gather and process more intelligence during missions. Radio cryptography modernization enables transition to next-generation mobile user objective system, satellite communications, providing secure, jam-resistant, beyond line-of-sight connectivity regardless of weather or tactical situation. These communication upgrades transform the B-1B from an isolated strike platform into a network node that can receive targeting data from satellites, drones, or other aircraft, immediately prosecute time-sensitive targets, and share battle damage assessment back to commanders. This networking capability multiplies effectiveness by allowing bombers to participate in dynamic targeting, where objectives change based on real-time battlefield developments rather than pre-planned strike packages that might hit obsolete aim points. The decision to regenerate retired B-1Bs from the boneyard at Davis-Monthan Air Force Base demonstrates commitment to maintaining fleet strength through the transition period. When a B-1B was severely damaged in a fire at Dyess Air Force Base in April 2022, causing nearly $15 million in damage, the Air Force faced a choice: invest in expensive repairs or replace the aircraft from storage. Officials chose to pull the retired bomber nicknamed Lancelot from the 309th Aerospace Maintenance and Regeneration Group, restore it to flyable condition, and return it to operational service. This regeneration process, while complex and time-consuming, proved more cost-effective than repairing fire damage and maintained the congressional mandate for a specific fleet size. The Air Force has indicated willingness to regenerate additional retired aircraft if operational requirements demand it, providing a reserve capacity that can be activated relatively quickly. The current operational fleet of approximately 45 B-1Bs, split between Ellsworth in South Dakota and Dyess in Texas, represents a carefully balanced force structure. Each bomb wing maintains roughly half the fleet, ensuring that even if one base is temporarily incapacitated by weather, maintenance, or other issues, the other can continue operations. This dispersal also complicates adversary targeting. Destroying American bomber capability requires successfully attacking multiple locations, rather than a single concentrated base. As additional bases, including Whiteman in Missouri, prepare to receive B-21 Raiders, the bomber force will become even more distributed, further enhancing survivability against preemptive strikes. Combat experience validates the B-1B's effectiveness and justifies continued investment. During Operation Absolute Resolve, the January 2026 mission that captured Venezuelan President Nicolas Maduro, B-1B Lancers played critical roles in suppressing air defenses and providing on-call strike capability for ground forces. Chairman of the Joint Chiefs Air Force General Dan Kane specifically mentioned B-1Bs among the 150 aircraft participating in the operation, noting their contribution to the overwhelming success that saw Maduro extracted without American casualties. Throughout 2025, Lancers deployed to the Middle East conducted successful counter-drone operations, destroying Iranian-supplied Shahed drones threatening American and allied forces, while also conducting precision strikes against Syrian military positions that threatened U.S.-backed fighters. The cost-effectiveness of the B-1B compared to alternatives makes continued operation economically rational despite high maintenance requirements. Flight hour costs run approximately $72,000 according to recent estimates, substantially less than the $135,000 for B-2 Spirit stealth bombers and competitive with the B-52's costs. When you consider that a single B-1B carrying 36 cruise missiles delivers firepower equivalent to 18 F-35 fighters each carrying 2 missiles, the economics become compelling. The fighter package would require multiple aerial refuelings, extensive mission planning, and coordinated timing, while a single bomber crew can execute the same strike with far less complexity. International observers are closely watching B-1B developments for insights into American capabilities and intentions. Allies operating under U.S. security guarantees, including Japan, South Korea, and NATO members in Europe, view bomber modernization as reassurance that America maintains credible conventional deterrence against aggression. The ability to rapidly deploy devastating firepower from standoff ranges without risking high-value assets like aircraft carriers provides options for responding to crises without automatic escalation to nuclear employment. Adversaries, conversely, must now plan their defenses around the assumption that American bombers can deliver overwhelming conventional firepower that could cripple military capabilities in the opening hours of conflict. Looking toward future capabilities, the B-1B continues evolving with potential integration of directed energy weapons, advanced electronic warfare systems, and even more sophisticated sensors. Research into laser defensive systems that could engage incoming missiles offers the possibility of active protection that would dramatically enhance survivability in contested airspace. Improved electronic warfare could degrade or destroy enemy air defense radars, creating corridors for penetration that currently don't exist. Advanced synthetic aperture radars could identify and track mobile targets like missile launchers or command vehicles, enabling dynamic retargeting that keeps pace with fluid battlefield conditions. The hypersonic testing mission places B-1Bs at the forefront of America's efforts to field operationally viable hypersonic weapons. While the initial air-launched Rapid Response Weapon program faced challenges and was reportedly canceled in 2023, the fiscal 2026 budget request for unspecified quantities of AGM-183A missiles suggests the program has been revived or reformulated. The United States has fallen behind China and Russia in fielding operational hypersonic systems, with both adversaries having tested and, in Russia's case, combat-employed such weapons. The urgency to close this gap drives investment in hypersonic development, and the B-1B serves as the primary testbed, ensuring these weapons can be rapidly fielded once testing validates performance. The Naval Strike Mission deserves particular emphasis, given the focus on potential conflict with China. The People's Liberation Army Navy has expanded dramatically over the past 2 decades, now fielding more warships than the United States and steadily improving quality. Chinese aircraft carriers, advanced destroyers equipped with sophisticated air defense systems, and amphibious assault ships capable of supporting invasion operations represent capabilities that didn't exist a generation ago. American planners must develop cost-effective methods to counter this naval expansion without bankrupting the defense budget through one-for-one matching. B-1Bs loaded with 36 LRASMs offer exactly this kind of asymmetric capability, where a relatively modest investment in bomber upgrades creates ship-killing potential that forces China to fundamentally reconsider naval employment. Militaries worldwide, particularly in China and Russia, are genuinely afraid of what these bombers can now accomplish. The comfortable assumptions that guided their defensive investments for decades have been shattered by American innovation, which has transformed an aging Cold War platform into a 21st century weapon system. As long as potential adversaries field targets that require destruction and maintain air defenses designed to counter traditional bomber capabilities, the B-1B Lancer will remain relevant and terrifying. The bone lives on, more dangerous than ever, carrying a message adversaries cannot ignore. American air power adapts, evolves, and will always find ways to accomplish the mission. In a world where technology shapes global power, the U.S. has made a major leap forward. The 2026 B-1 Lancer, a game-changing bomber, has just been revealed, promising to transform military aviation. And as global tensions rise, the arrival of this powerhouse signals a new chapter in America's military dominance. But what makes this aircraft truly unmatched? Join us as we uncover what makes the U.S. 2026 B-1 Lancer a true force to be reckoned with. The roots of the B-1A program stretch back to the early 1960s, a pivotal era for U.S. military aviation. This was shortly after a chilling wake-up call for American intelligence, the infamous downing of the Lockheed U-2 Dragon Lady. That high-altitude reconnaissance aircraft was shot out of the sky by the Soviet Union, exposing vulnerabilities in U.S. aerial operations. This incident shook the U.S. intelligence community to its core and forced a major overhaul of policies, procedures, and safety protocols. In response, military planners envisioned an ambitious new bomber. The idea was to combine the immense payload and range capabilities of the legendary Boeing B-52 Stratofortress with the blistering speed of Mach 2, similar to the sleek Convair B-58 Hustler. The hope was that such a bomber would outclass anything the Soviet Union could throw at it, essentially rendering their defenses powerless. But this dream collided with a harsh reality. The SA-2 guideline missile, known to the Soviets as the S-75 Dvina, a game-changing surface-to-air missile system that proved devastatingly effective. It was this very missile that brought down the U-2, shattering any illusions of invincibility in high-altitude operations. The United States quickly realized that the age of safe, high-speed, high-altitude bombing was over. In a radical pivot, military strategists decided to change the game entirely. Instead of soaring above enemy defenses, bombers would dive down low, hugging the terrain to evade radar detection. This approach, known as low-altitude penetration, took advantage of terrain masking, a clever tactic where pilots used natural features like hills, valleys, and even mountains to hide from radar. By flying low, bombers could disrupt the line of sight between enemy radar systems and the aircraft, essentially playing a high-stakes game of hide-and-seek. The terrain acted as a shield, making it nearly impossible for radar operators to maintain a lock on the bomber. Interestingly, this shift toward low-altitude flying began even before the U-2 incident, showing just how rapidly tactics were evolving in the face of new threats. In those early days of radar technology, one major challenge was how the systems often struggled to detect enemy aircraft, especially those flying at low altitudes. This problem was made even worse by random reflections from the ground and nearby objects, which created significant interference. These limitations greatly reduced the effectiveness of air defense systems when dealing with low-flying aircraft. Take the B-52 Stratofortress, for example. This iconic bomber was originally designed for high-altitude missions, cruising far above the reach of most enemy defenses. However, its remarkable adaptability turned it into an effective low-altitude workhorse over time. Its massive fuel capacity allowed it to fly long distances even at lower levels, while its large airframe provided ample room for advanced radar jamming equipment and deception systems. These upgrades helped it counter enemy radars and stay relevant despite its aging design. That said, the B-52 was never truly ideal for low-altitude missions. Its size and design made it less maneuverable compared to purpose-built low-flying aircraft. Recognizing this limitation, the U.S. Air Force sought a more specialized solution: a strategic penetration bomber capable of evading enemy radar by hugging the terrain. The first comprehensive study of such an aircraft, called the Subsonic Low-Altitude Bomber, was completed in 1961. This led to the conceptualization of a revolutionary design. Unlike the rugged, militaristic appearance of traditional bombers, this new design looked more like a commercial airliner, with sleek, swept-back wings, a distinctive T-shaped tail, and massive high-bypass turbofan engines for greater fuel efficiency and range. The story of the Advanced Manned Strategic Aircraft began with a predecessor project known as the URSA Extended Range Strike Aircraft. This ambitious endeavor introduced a revolutionary design feature: a variable sweep wing, allowing the aircraft to adapt its wing position during flight for better performance at different speeds. It quickly gained attention within the aviation industry, becoming a significant milestone in aircraft innovation. The URSA project set some bold goals. The aircraft needed to carry a payload of 10,000 pounds and travel more than 10,000 miles. Of this distance, nearly 2,900 miles were to be flown at low altitudes, a challenging requirement given the fuel efficiency and structural demands of such flights. By 1963, all these ambitious ideas coalesced into what became the Advanced Manned Precision Strike System, or AMPS. This program sparked intense research and development efforts, with industry giants like Boeing, General Dynamics, and North American Aviation stepping up to the challenge. A year later, the U.S. Air Force revised its requirements, giving the concept a new name and broader ambitions: the Advanced Manned Strategic Aircraft. Unlike its predecessor, AMSA prioritized high-speed, high-altitude flight capabilities, aiming to compete with the likes of the Mach 2-capable F-111 Aardvark bomber already in service. This change was driven by the need for a bomber that could operate effectively in both conventional and nuclear missions, potentially outmaneuvering emerging Soviet air defenses. By this time, AMSA had become somewhat of a running joke among aviation experts, who quipped that it was America's most studied aircraft. While the project promised innovation, it also highlighted a growing debate within U.S. defense circles. Then Secretary of Defense Robert McNamara was particularly skeptical. A staunch advocate of intercontinental ballistic missiles as the backbone of America's nuclear deterrence, McNamara argued that pouring resources into developing a costly new bomber was unnecessary. After all, ICBMs could deliver similar results at a fraction of the cost and with far fewer operational risks. In 1964, the Advanced Manned Strategic Aircraft program took a significant turn when it was scaled back to focus solely on component research and development. This decision reflected broader debates about defense priorities during that era. By 1968, the program faced another setback when funding for the aircraft's development was vetoed yet again. However, everything changed when Richard Nixon became president. Shortly after taking office, Nixon reinstated the AMSA program as part of his administration's flexible response strategy. This approach was designed to provide a wide range of military options, steering away from the stark choice of launching an all-out nuclear war. Nixon's Secretary of Defense, Melvin Laird, took a closer look at the program. After a thorough review, he made some pivotal adjustments. One notable decision was reducing the number of FB-111 aircraft, which fell short of the range required for strategic missions. Instead, Laird pushed for accelerated research and development on the AMSA design, aiming to deliver a long-range bomber that could better meet the Air Force's needs. By 1969, after extensive discussions and debates, the program finally gained traction. It was officially named the B-1A project, signaling a fresh chapter in the Air Force's quest for a cutting-edge bomber. That same year, the Air Force invited aerospace giants, Boeing, General Dynamics, and North American Rockwell, to submit their proposals for what would become a new generation of strategic bombers. The process wasn't without its challenges. By 1971, after reviewing North American Rockwell's proposed designs, the Air Force identified 297 requests for design changes. These revisions range from addressing issues of non-compliance with technical specifications to making improvements that would simplify maintenance and enhance operational efficiency. Despite these hurdles, the program pressed on, laying the foundation for what would eventually become the iconic B-1 Lancer. One of the major challenges facing the B-1 bomber program in the 1970s was inflation, which drastically inflated costs. When the program was first conceived, the estimated cost of building one B-1 bomber was around $40 million in the 1970s. However, by 1975, that figure had skyrocketed to $70 million, nearly double the original estimate. This sharp increase in expenses prompted President Jimmy Carter to reevaluate the entire program. But it wasn't just the soaring costs that concerned him. Around the same time, President Carter learned about ongoing work on a groundbreaking stealth aircraft. The concept of a nearly undetectable bomber using advanced stealth technology seemed like a smarter investment to him compared to the continuing development of the B-1. On June 1977, Carter made a tough decision that he later described as one of the hardest of his presidency. He announced the cancellation of the B-1A bomber program. Instead of pouring more money into the B-1, his administration chose to focus on strengthening the U.S. nuclear deterrent through intercontinental ballistic missiles and submarine-launched ballistic missiles, which were seen as more cost-effective and strategically valuable at the time. Despite the secrecy surrounding the stealth bomber program, Carter's decision allowed for the continuation of the Advanced Technology Bomber Project. This highly classified program would later give rise to the iconic B-2 Spirit, a stealth bomber that revolutionized aerial warfare with its ability to penetrate deep into enemy territory undetected. Interestingly, even though the B-1A program was officially canceled, flight testing of the prototypes continued. By the time testing ended in April 1981, 4 B-1A prototypes had completed 70 test flights, logging a total of 378 flight hours. These tests provided valuable data that would prove useful when the program was eventually revived. When President Ronald Reagan took office in 1981, he faced a similar dilemma: whether he should restart the B-1 program to quickly enhance the U.S. bomber fleet, or he should wait for the ATB project to deliver a more advanced stealth bomber. By October 1981, President Ronald Reagan made a bold announcement. The U.S. would move forward with an order for 100 B-1 bombers to fulfill the critical long-range combat aircraft role. Just a few months later, in January 1982, the U.S. Air Force took the next big step, signing 2 contracts with Rockwell International worth a hefty $2.2 billion. These contracts kicked off the development and production of this cutting-edge fleet of bombers. But this wasn't just a revival of the earlier B-1A model. It was the dawn of a reimagined aircraft, the B-1B Lancer. Engineers made significant changes to improve performance and survivability. For example, the original variable geometry air intake ramps, which were complex and heavier, were replaced with simpler fixed intake ramps. This change not only streamlined the aircraft, but also reduced its radar cross-section, making it less detectable by enemy radar systems. While this came with a slight reduction in maximum speed, the trade-off was worth it. The redesign prioritized high subsonic speeds at low altitudes, a critical capability for evading detection and enemy fire during missions. The B-1B could now cruise at Mach 0.92 at low altitudes, an improvement over the B-1A's Mach 0.85. For operations at higher altitudes, its top speed reached Mach 1.25, slightly below the supersonic capabilities of its predecessor, but still impressive for a strategic bomber. Another critical enhancement was its maximum takeoff weight, which jumped from 395,000 pounds in the B-1A to a staggering 477,000 pounds in the B-1B. This upgrade allowed the aircraft to take off fully loaded with internal fuel and still carry additional external weapons if needed. This made the B-1B not just a stealthier bomber, but also a far more versatile and capable one, perfectly suited to handle Cold War-era threats. Due to the dedicated work of Rockwell engineers, the B-1 bomber's weight increase was kept to a minimum, despite major upgrades and design changes. One key factor was the growing concern about the Soviet Union's introduction of the MiG-31, which was equipped with the advanced Zaslon radar system, along with other aircraft capable of look-down capabilities. To counter these threats, the B-1's electronic warfare suite underwent a significant modernization, improving its ability to avoid detection and jamming. The B-1's impressive appearance of the aircraft features a mixed-wing configuration, with a variable sweep wing that can adjust from 15 to 67.5 degrees. This gives it great versatility, allowing it to perform at both high and low speeds with excellent maneuverability. The B-1 also boasts unique triangular motion control keels and a distinctive crosstail design. Underneath the sleek exterior, the bomber is powered by 4 General Electric F101GE102 turbofan engines. Each engine is capable of producing 17,390 pounds of thrust, with afterburners providing an impressive 3,780 additional pounds of thrust for rapid acceleration. In 2004, during discussions about the B-1B to B-1R upgrade, there were plans to replace these engines with the more modern Pratt & Whitney F119 engines, similar to those used in the F-22 Raptor. While the idea was floated by Lockheed Martin, it never progressed to the implementation stage. The survival of the B-1 bomber, especially when compared to its contemporaries in the aviation world, can largely be credited to its relatively low radar signature, or effective dispersion area. While it's far from being a stealth aircraft like the B-2 Spirit, the B-1's design cleverly incorporates features that reduce its radar visibility. For instance, it boasts serpentine-shaped air intakes that help minimize radar reflections and extensive use of radar-absorbing materials on its fuselage. These innovations give the B-1 an ESR that is approximately 1/50 of that of the B-52, even though both aircraft are roughly the same size. To put it simply, the B-1's radar signature is closer to that of a smaller, less detectable aircraft, though it doesn't fully qualify as stealth. Dubbed the Bone, the B-1B Lancer was a formidable threat during its heyday, especially to the Soviet Union. With a staggering range of over 3,400 miles without needing refueling, the bomber could extend its reach indefinitely thanks to its in-flight refueling capability. Its payload capacity was equally impressive, capable of carrying up to 125,000 pounds of bombs, including nuclear warheads. This meant the B-1B could deliver devastating strikes anywhere on the planet with speed and precision. However, timing was not on the B-1 side. When it officially entered service in the late 1980s, the Cold War was winding down, and the collapse of the Soviet Union soon after left the bomber without its primary mission. By 1992, the dissolution of the Strategic Air Command led to the removal of the B-1's nuclear capabilities. From that point onward, the fleet was repurposed exclusively for conventional missions. But the B-1 wasn't destined to fade into irrelevance. The integration of advanced technologies, such as Lockheed Martin's Sniper Advanced Targeting Pod, gave the aircraft a second life. This upgrade allowed the B-1 to deliver precision strikes with modern smart munitions, effectively transforming it into a critical component of 21st century warfare. When the B-1B Lancer bomber made its debut in Operation Desert Fox in Iraq back in 1998, it showcased its effectiveness with what some called a dumb bomb. Despite being a relatively simple weapon, the B-1B's ability to deliver it with remarkable accuracy completely redefined its role on the battlefield. Originally designed as a Cold War-era strategic bomber, it got a fresh lease on life as a versatile close air support aircraft, proving to be an unexpected hero in the rugged and expansive terrains of Iraq and Syria. The B-1 Lancer has played a critical role in several major military operations, including Operation Allied Force in Kosovo, Operation Enduring Freedom in Afghanistan, and the 2003 invasion of Iraq. Known for its versatility, the B-1 has delivered a wide array of conventional weapons in combat zones, with the 2,000-pound GBU-31 JDAM standing out as one of its most frequently deployed munitions. During the early stages of Operation Enduring Freedom, the B-1 demonstrated its significant contribution to aerial warfare. In just the first 6 months, a fleet of 8 B-1s dropped nearly 40% of all aerial bombs used in the campaign, including an impressive 3,900 JDAMs. These precision-guided munitions were also pivotal in Iraq, where, on April 7, 2003, B-1 bombers participated in a high-profile mission to target Saddam Hussein and his 2 sons, though the attempt was ultimately unsuccessful. The B-1's reliability improved notably during its service in Afghanistan, achieving a mission-capable rate of 79%, a significant milestone given the demanding operational environment. Originally, 100 B-1Bs were built, but by year 2000, 93 remained, with the others lost to accidents. In 2001, the Pentagon proposed placing about 1/3 of the fleet in storage as part of a cost-saving measure. This sparked intense opposition from U.S. Air National Guard officers and members of Congress, leading to the drafting of an amendment to block the cuts. The proposal was aimed at reallocating funds to modernize the remaining aircraft, focusing on upgrades like advanced computer systems to maintain the bomber's cutting-edge capabilities. In 2003, the U.S. Air Force made a strategic decision to retire 33 of its B-1B Lancer bombers, focusing its resources on keeping the rest of the fleet in top operational condition. This move followed the removal of B-1B from the Air National Guard's 2 bomb wings, allowing the military to allocate its budget more efficiently. However, the following year brought a shift in priorities. A new appropriation bill called for some of these retired aircraft to be reactivated. As a result, 7 B-1Bs were pulled out of storage, bringing the fleet back up to 67 aircraft. By July 2007, the B-1B had taken on a vital new role. The Associated Press highlighted the growing USAF presence in Iraq, where the B-1B had been reintroduced as a crucial support platform for coalition ground forces. Its versatility and endurance made it ideal for armed overwatch missions. Starting in 2008, B-1Bs were deployed over Iraq and Afghanistan, circling above combat zones to provide real-time surveillance and immediate air support. Equipped with precision-guided bombs, these bombers could strike enemy targets on demand, significantly boosting ground troops' effectiveness. In addition to combat roles, the B-1B was also at the forefront of aviation innovation. On March 19, 2008, a B-1B from Dallas Air Force Base, Texas, made history by becoming the first USAF aircraft to reach supersonic speeds using a blend of synthetic and petroleum-based fuel. This groundbreaking test, conducted over Texas and New Mexico, was part of a broader initiative to reduce the military's dependence on traditional oil supplies while exploring cleaner, more sustainable energy options. Later that year, on August 4, 2008, a B-1B equipped with the Advanced Sniper Targeting Pod completed its first combat mission. This cutting-edge technology allowed the crew to identify enemy positions with pinpoint accuracy and successfully deploy a GBU-38 guided bomb in Afghanistan. This mission underscored the bomber's evolution into a precision strike platform capable of adapting to modern warfare's demands. The B-1B continued to demonstrate its global reach and versatility. In March 2011, B-1Bs from Ellsworth Air Force Base participated in Operation Odyssey Dawn, striking undisclosed targets in Libya, One of the B-1B standout features is its massive fuel reserves, allowing it to stay airborne for hours on end. This endurance gave it the ability to circle above targets, providing real-time reconnaissance that became crucial for both headquarters and troops engaged in ground operations. The B-1B wasn't just about loitering, though. Equipped with advanced systems like the Sniper Advanced Targeting Pod, it could precisely locate and relay targeting information. Whether guided by data from ground troops or its onboard systems, it could drop thousands of pounds of explosives with pinpoint accuracy, devastating enemy positions, and supporting allied forces in some of the most challenging combat scenarios. Interestingly, the B-1B's potential to carry external weapons was part of its original design during the Cold War. However, due to the Strategic Arms Reduction Treaty, this capability was shelved as part of international disarmament efforts. Fast forward to recent years, this feature has been revived, enabling the aircraft to carry up to a dozen powerful external weapons. This modernized capability enhances its flexibility, ensuring it remains a critical asset in modern warfare. One of the B-1's most notable upgrades is the addition of AGM-158 Joint Air-to-Surface Standoff Missiles and AGM-158C long-range anti-ship missiles. These subsonic cruise missiles are designed to strike from significant distances, allowing the B-1 to neutralize targets with precision while staying out of the range of enemy defenses. The B-1's load-adaptable modular pylon system is a game-changer. It enables the aircraft to carry an impressive total of 36 cruise missiles, 12 on its external pylons, and up to 24 more inside its internal bomb bays. This capacity transforms the B-1 into a powerhouse capable of overwhelming enemy naval forces, particularly in high-stakes scenarios like a conflict in the Asia-Pacific theater, where China's growing naval presence poses a strategic challenge. The B-1 is also gearing up to carry hypersonic weapons, which are currently under active development. Hypersonic missiles, such as the Hypersonic Attack Cruise Missiles, boast remarkable capabilities, including operational ranges of approximately 1,000 miles and mind-boggling speeds of up to Mach 8, 8 times the speed of sound. These missiles are so advanced that they can outpace most existing defense systems, making them nearly impossible to intercept. What makes the B-1 particularly unique is its ability to carry up to 12 hypersonic missiles externally, a feature that significantly boosts its firepower. This combination of advanced cruise and hypersonic missiles positions the B-1 Lancer as a crucial asset in any future military campaign, especially in deterring or countering threats from the People's Republic of China in the increasingly contested waters of the Asia-Pacific region. Originally, this list also included the AGM-138A Air-Launched Rapid Response Weapon, a key component of the Aero Hypersonic Missiles program. However, the U.S. Air Force canceled the development of these hypersonic missiles on March 2023 due to a combination of budget constraints and shifting priorities. Despite the cancellation, the U.S. Air Force still has a remarkable and potent conventional weapon system in its arsenal. If the Air Force manages to equip its remaining 45 B-1 Lancer bombers with the necessary missiles and secure sufficient government funding, it will wield one of the most powerful conventional weapons combinations ever seen. Just 5 B-1 Lancer bombers, crewed by only 15 people, can destroy 6 warships with a combined crew of more than 3,000 sailors. This is an extraordinary efficiency ratio, one that rivals even nuclear weapons in its destructive potential. The B-1 is capable of carrying a wide range of conventional bombs and missiles, including precision-guided munitions, which can be launched from great distances. The B-1's massive payload capacity and ability to fly at high speeds make it a key component of America's airstrike capabilities. And while this kind of power is formidable, it's important to note that even the most advanced aircraft, like the B-1, will eventually need to be replaced. In 2032, the Pentagon plans to begin gradually replacing the B-1 with the cutting-edge B-21 Raider stealth bomber produced by Northrop Grumman. The B-21 is designed with stealth features that allow it to penetrate even the most sophisticated enemy air defense systems. It's intended to be more efficient, cost-effective, and adaptable to future technological needs. Despite this, there's a strong belief among military analysts that the B-1 Lancer could remain relevant far beyond its expected retirement date. With additional upgrades to its avionics, weapon systems, and engine performance, it could continue to perform critical roles in the U.S. Air Force's missions until at least 2040. The B-1's ability to carry 75,000 pounds of bombs and missiles, more than any other U.S. bomber, is one of the reasons it remains so valuable. It can be equipped with a variety of weapons, including joint direct attack munitions, which give it precision strike capabilities, and it can carry out strategic and tactical bombing missions with exceptional effectiveness. Furthermore, despite its age, the B-1 has been continuously upgraded to maintain its relevance in the modern battlefield, with advanced radar, electronic warfare systems, and more. The legendary B-2 Spirit stealth bomber has returned with groundbreaking upgrades that push the limits of military technology. Once a Cold War secret, it's now been transformed into a weapon that feels decades ahead of its time. From hypersonic readiness to futuristic invisibility, this aircraft has left rival nations scrambling to catch up. Why are experts calling it the most advanced bomber in history? And what does its rebirth mean for the future of global defense? Join us as we uncover the secrets behind the upgraded B-2 Spirit. The B-2 Spirit stealth bomber has just received a round of upgrades that defense analysts describe as almost unbelievable for an aircraft that first flew more than 3 decades ago. What was once a Cold War marvel has now been reshaped into something that feels designed for the next generation of warfare. At the heart of this modernization effort is a system called Spirit Realm 1, or SR-1. With this open mission system setup, the bomber can take on new weapons and functions through simple software updates instead of requiring costly hardware changes. Thanks to this framework, the Air Force can integrate advanced munitions, such as the GBU-72 bunker buster, and may even prepare the platform to carry hypersonic missiles, all without dismantling the aircraft. Engineers took a very different approach with this upgrade. By adopting what they refer to as a software factory model, teams are now able to design, test, and roll out new features at a speed that would have been unimaginable in the past. This method reduces defects, speeds up development, and ensures that the new features work seamlessly alongside the B-2's existing avionics. The cockpit has been updated as well. Pilots now work with improved displays that provide real-time battlefield information, helping them plan missions more efficiently and react faster while in the air. Communication systems have been modernized as well, replacing the old single-channel setup with a system that supports simultaneous voice and data transmission. One of the most critical improvements came from advances in satellite communications. Through beyond line-of-sight connectivity, crews are now able to get real-time updates on targets and shifting mission requirements, even when operating deep inside contested airspace. This level of in-flight adaptability greatly improves overall mission flexibility. At the same time, stealth remains the B-2's defining advantage, and engineers have continued working to make it even more effective. A specialized survivability team has introduced both hardware and software enhancements to sharpen the bomber's radar cross-section signature. These tools give pilots the ability to detect, locate, and classify enemy air defense systems while still preserving their low visibility profile. This round of changes builds on earlier efforts under the Defensive Management System Modernization Program, which upgraded the aircraft's electronic warfare suite. The B-2 can now detect and classify threats while also gathering valuable electronic intelligence, all while remaining cloaked from radar. The timing of these developments is no accident. Both Russia and China have spent years designing advanced radar networks and missile systems specifically aimed at countering stealth technology. Keeping the B-2 ahead of those capabilities is vital, especially since the aircraft continues to serve as America's only long-range penetrating strike bomber. Today, just 19 B-2s remain in service after the loss of 2 aircraft in earlier incidents. Each one undergoes a full overhaul roughly every 9 years, which includes structural maintenance and the reapplication of radar-absorbing coatings. Because the fleet is so small, extending the life and relevance of each aircraft is considered essential for maintaining the United States' ability to strike targets anywhere in the world. The B-2 can deliver up to 40,000 pounds of conventional or nuclear weapons and, with aerial refueling, can reach intercontinental targets without detection. Until the new B-21 Raider enters service later this decade, the Spirit remains the backbone of America's deep strike capability. The Spirit Realm 1 program makes sure the bomber doesn't fall behind. By relying on continuous software upgrades rather than major redesigns, the Air Force can keep the B-2 responsive to evolving technologies and threats. Defense officials believe these changes will keep the bomber viable well into the 20s. The flying wing design that once looked decades ahead of its time has now been adapted again, proving that a concept born in the 1980s can still set the standard for next-generation aviation. The most expensive military aircraft ever built has now advanced to a point where it seems to defy the very rules of radar detection. How can a machine larger than half a football field disappear from the most sophisticated surveillance systems in the world? The B-2 Spirit achieves a kind of invisibility that once seemed impossible. Radar operators facing the aircraft often find their screens showing nothing but empty sky. Despite being 69 feet long with a wingspan of 172 feet, the bomber can appear no larger than a small bird on advanced detection equipment. The foundation of this ability lies in its design. Unlike older bombers that rely on vertical fins and sharp edges, the B-2 was designed as a seamless flying wing. The design of the aircraft forces radar signals to scatter in multiple directions instead of bouncing straight back to enemy stations, which makes the bomber much harder to track. Equally important is the special coating that covers the entire surface. This material absorbs those signals and disperses the energy as heat rather than sending it back to detection systems. Maintaining that protective layer is a constant challenge. Each bomber must be kept in climate-controlled hangars, and about every 9 years, the aircraft goes through a major depot cycle where technicians carefully strip and reapply the coating to preserve its stealth. The process costs millions of dollars per aircraft, but without it, the B-2 would quickly lose the low visibility that makes it so valuable. Even the engines were designed with stealth in mind. 4 General Electric F118 engines sit hidden within the wing itself. The air intakes use curved ducts that block radar waves from reaching the turbine blades, which would otherwise light up on detection systems. Exhaust nozzles mix hot gases with cooler outside air to cut down on heat emissions, lowering the aircraft's infrared signature. Heat-absorbing tiles, similar to those once used on the space shuttle, line critical areas of the bomber. These prevent heat tracking systems from locking onto the B-2 even when it operates at altitudes above 50,000 feet. Another remarkable feature is its contrail management system. Most high-altitude aircraft leave long vapor trails that give away their position. The B-2 can suppress contrail formation when necessary, erasing this common giveaway during sensitive missions. Stealth systems come together through what pilots call penetration mode, activated by a button marked PEN. Once engaged, this mode synchronizes all of the bomber's stealth technologies to minimize signatures across radar, infrared, and visual detection. Enemy radar crews often report nothing more than background noise when the B-2 is in this state. The idea of a flying wing is not new. Jack Northrop tested the concept with his YB-49 prototype back in 1947, which had the same wingspan as the modern B-2. Even Germany experimented with a similar design during World War II, building the Horten-Ho 229, but their version lacked the advanced materials and precision engineering that would make the American design truly practical. The science behind the B-2's stealth owes much to Soviet research. In 1962, Russian physicist Pyotr Ufimtsev released groundbreaking research on the way electromagnetic waves interact with different surfaces. His work was meant as pure science, but American engineers later applied those principles to develop the B-2's unique radar-deflecting shape. What began as a theory in a textbook eventually became the foundation for an aircraft designed to slip past Soviet air defenses. The result was the B-2 Spirit, a bomber that blends geometry, radar-absorbing coatings, hidden engines, and thermal management into a single design. Together, these features make it extraordinarily difficult to detect with conventional tracking methods. For air defense crews, the reality is simple. It is nearly impossible to shoot down something you cannot see, hear, or lock onto. Even with all the advanced stealth technology built into the B-2, the aircraft itself is useless without the right person in the cockpit. But what exactly makes someone qualified to fly America's most secret bomber? Since the B-2 Spirit program began, fewer than 300 pilots have ever been trusted to fly it. That number is shockingly small when you consider the size of the United States Air Force. It is often described as the most selective flying group in military history, with acceptance rates so low that even the Navy SEALs seem easier to get into. Getting selected is about much more than raw flying skills. Each candidate goes through psychological testing that digs far deeper than the usual pilot requirements. Military doctors look at personality traits, stress tolerance, and even how well someone can get along with others. Missions can last close to 2 full days, with 2 people locked inside a tight cockpit. The Air Force cannot risk putting 2 pilots together if there's even a chance they might clash or buckle under pressure. Physical skill is just as important. B-2 pilots must have excellent reflexes and steady hands, especially for tasks like refueling in the air, which requires near-perfect precision. The B-2 doesn't fly like any other plane. It has unusual flying wing aerodynamics that demand special handling skills. Learning to control it means starting almost from scratch, even for experienced pilots. On top of that, the security checks are among the strictest in the military. Candidates face background investigations that cover their personal history, family ties, and even their finances. The government wants to be sure that no one flying the B-2 could be blackmailed or bribed into betraying sensitive secrets. Training is another hurdle. Before touching the actual bomber, pilots spend months inside advanced simulators that recreate every system, warning light, and emergency the plane might face. Instructors throw constant challenges at them: engine failures, electrical problems, combat situations, and even extreme weather. Only those who make quick, smart decisions under stress can move forward. Mission commanders receive extra instruction beyond just flying. They are trained in weapons use, navigation, and electronic countermeasures that protect the bomber from enemy defenses. While the pilot focuses on flying, the commander handles the systems. Success depends on both working seamlessly as a team during missions that can stretch almost 2 days without landing. The B-2's cockpit is designed differently from most military aircraft. Instead of sitting one behind the other, both crew members sit side by side in ejection seats. This makes long flights easier to manage because communication is more natural. However, it also forces pilots to adapt to a wider forward view that feels very different compared to other planes. All B-2 flights operate out of one location, Whiteman Air Force Base in Missouri. The base has specially built hangars that control temperature and humidity to protect the bomber's delicate stealth coating. Pilots often spend weeks at a time training or preparing for missions, which means long stretches away from family. Interestingly, most B-2 pilots only fly a handful of missions each year. The bomber fleet is small, and each aircraft is unique. To stay sharp, pilots rotate between different planes so they remain familiar with how each one handles. For many, flying the B-2 represents the peak of their career. Once they retire from the program, they often don't move on to fly other aircraft because of how specialized the training is. Instead, some stay connected to the bomber community by working as instructors or taking contractor roles that support the program. The limited number of trained pilots poses challenges for the Air Force. Whenever the bombers are needed, commanders must carefully balance mission schedules, rest time, and training requirements. Each pilot represents years of investment and cannot be replaced quickly. It is this scarcity, along with the difficulty of the training, that makes the B-2 community one of the most exclusive groups in the entire United States military. These top pilots showed their true skill in missions that are still studied by military experts today. But here's the question: how could just 2 bombers completely change the way wars are fought from the sky? The B-2 bomber made its combat debut over Kosovo in 1999, and it instantly rewrote the rules of air warfare. 2 bombers flew missions that lasted 31 hours straight, leaving from Whiteman Air Force Base in Missouri, striking their targets in the Balkans, and flying back without stopping anywhere in between. Even though the B-2 made up less than 1% of all combat flights during Operation Allied Force, it destroyed nearly 1/3 of the priority targets in just the first 8 weeks of the conflict. Military leaders had never seen anything like this. Normally, hundreds of planes and multiple waves of attacks were needed to get the same results. The B-2 managed to do in one mission what entire groups of aircraft struggled to accomplish. The bomber named Spirit of America set a record during Operation Enduring Freedom in 2001. It flew the longest combat mission in history, 44 hours non-stop from Missouri to Afghanistan and back. The engines never even shut down during a quick 45-minute crew change, after which the aircraft immediately launched again for another 30-hour flight. In total, it stayed in continuous operation for more than 70 hours. Each B-2 carried up to 40,000 pounds of guided bombs and smart weapons on these missions. These weapons were so accurate that commanders on the ground reported that the B-2 was able to hit high-value targets that other aircraft couldn't touch. Because the missions were so long, refueling in the air was essential. Every 6 hours or so, a KC-135 tanker would meet the bomber high above enemy territory to transfer fuel. Both aircraft had to fly in perfect sync for the transfer to work, making it one of the most delicate parts of the mission. The B-2 quickly became the aircraft trusted to strike first. It opened operations in Iraq, Afghanistan, and Libya by slipping into heavily defended airspace that other aircraft couldn't enter safely. Once the B-2 had destroyed key defenses, other planes could follow. Today, this first strike role is standard military practice. What made the B-2 so valuable was its ability to hit any target in the world within hours of being ordered. It didn't need bases in other countries or staging areas closer to the fight. It could launch straight from the United States and still complete its mission. Its advanced navigation systems meant it could fly and strike accurately in any conditions. Using radar and GPS-guided bombs, it could hit through thick clouds, heavy storms, or complete darkness. Enemies learned that bad weather could no longer protect them. Each mission proved that the billions spent on stealth technology and long-range strike power had been worth it. The B-2 showed it could achieve major objectives while putting very few aircrew at risk and with minimal civilian casualties. Planning these missions was just as demanding as the flights themselves. Crews spent hours studying maps, enemy defenses, weather, and backup targets before even stepping into the cockpit. Sometimes the planning lasted longer than the actual flight. After the missions, reviews showed the same results again and again. The B-2 hit its targets more effectively than traditional bombing campaigns, while needing far fewer aircraft and weapons to do the job. Despite its remarkable record in combat, America's most advanced bomber faces a serious challenge that could weaken national security. The question is simple but troubling. Why are these rare aircraft disappearing one after another? Back in the Cold War years, the United States planned to build 132 B-2 Spirit bombers. Defense companies prepared for huge orders, expecting that the cost per aircraft would drop once production ramped up. The goal was to create a fleet big enough to eventually take the place of the older B-52 bombers. But history shifted. In 1989, the same year the B-2 took its first flight, the Berlin Wall fell. The Soviet Union collapsed soon after, and with it the need for such a large stealth bomber force. Congress slashed the order from over 100 to just 21 planes. That decision made each B-2 incredibly expensive, more than $2 billion apiece. With so few built, every aircraft became almost like a custom project, each with its quirks and demanding upkeep. Since entering service, the fleet has lost 2 bombers. In 2008, the Spirit of Kansas crashed during takeoff in Guam after faulty sensors caused it to lift its nose too sharply. The crew ejected safely, but the aircraft was destroyed, just like that. America lost 4% of its stealth strike power. Another bomber, the Spirit of Washington, caught fire during maintenance at Whiteman Air Force Base in 2010. Workers accidentally set off a blaze that damaged the bomber's delicate structure and stealth coating. The Air Force debated for years whether fixing it was even possible before finally bringing it back to service. In 2022, another B-2 was badly damaged in a fire and written off completely. That incident left only 19 operational bombers, each one now an irreplaceable part of America's long-range strike force. To keep them flying, every B-2 goes through a deep overhaul about once every 9 years. This isn't routine maintenance, it's a complete rebuild. Workers strip off and reapply the radar-absorbing coating, upgrade the electronics, and replace or repair major systems. Each cycle costs hundreds of millions of dollars and takes months before the plane can return to duty. The aircraft are stored in special climate-controlled hangars at Whiteman Air Force Base in Missouri. The stealth coating is so sensitive that both temperature and humidity must stay within strict limits. If exposed to bad weather or stored incorrectly, the coating can break down, making the bomber easier to spot on radar. Building the B-2 in the first place meant inventing new ways of making things. Northrop Grumman developed advanced composite materials, custom tools, and entirely new assembly techniques just for this program. Once the final bomber rolled out, those production lines were shut down. That means no more B-2s can ever be built with the same methods. Looking ahead, the Air Force plans to keep the B-2 in service until the new B-21 Raider is ready in larger numbers. The Raider is designed with modern materials and updated production techniques, and it also draws on lessons learned from the B-2 program. The first B-21 bombers are expected to be combat-ready later in the decade. For now, though, the B-2 remains the only aircraft that can slip past the world's toughest air defenses and strike anywhere on the globe. Losing even one more reduces America's reach and weakens its ability to respond to threats far from home. The United States just revealed a bomber so secret that even Congress does not know what it can do. And within weeks, Russia accelerated weapons programs. This is not a fighter jet. The B-21 Raider was built to enter airspace undetected and fly nuclear missions with just one pilot. Why are adversaries building defenses against a threat they cannot see, and what forced them to rethink decades of planning? Join us as we find out why the B-21 has Russia genuinely panicking. For decades, Russia and China constructed their air defense networks around one core assumption. They understood American bomber capabilities. Massive radar arrays blanketed contested regions. Surface-to-air missile batteries were positioned to intercept known flight profiles. Military strategists mapped scenarios based on the B-2 Spirit, a stealth bomber with limitations they'd studied exhaustively and believed they could counter. Then the B-21 was revealed, and that assumption was shattered. The geopolitical chessboard shifted. China rehearses military operations around Taiwan with alarming frequency. Russia demonstrated in Ukraine that modern warfare extends far beyond traditional battlefields into cyberspace and the electromagnetic spectrum. Coordinated autonomous systems now determine outcomes as decisively as bombs. America's existing bomber fleet, despite its raw power, was designed for a strategic environment that no longer exists. The B-2 Spirit costs over $150,000 per flight hour and requires 51 hours of maintenance for every hour airborne. It cannot be serviced outside specialized, climate-controlled facilities, which limits where and how often it can operate. Each mission demands months of preparation, coordination, and post-flight restoration, reducing flexibility during crises. Strategic deterrence only functions when adversaries believe a weapon will be used, and when a stealth bomber is too costly and fragile for sustained operations, its deterrent value becomes theoretical rather than operational. It serves like a conventional aircraft, using standard hangars and requiring hours instead of months. More critically, it was designed from inception to dominate an integrated battle space where cyber warfare, electronic attacks, drone swarms, and hypersonic missiles converge simultaneously. Here is what genuinely concerns Russian and Chinese military planners. This is not an experimental platform trapped in testing phases. 3 aircraft already exist, and production facilities are manufacturing 7 to 8 additional bombers each year, with a planned fleet of 100. This means operational squadrons will form while adversaries are still validating prototypes. By the time Russia fields the PAKDA and China introduces the H-20, dozens of B-21s will already be deployed, with crews logging thousands of flight hours, developing tactics, integrating new software, and identifying weaknesses long before opponents encounter the aircraft in conflict. Russia invested enormous resources in constructing air defenses optimized for known platforms, known signatures, and predictable mission profiles. Those systems were built on assumptions that no longer hold. As the B-21 enters service, entire layers of that defensive architecture risk becoming obsolete before reaching full operational maturity. Meanwhile, Chinese military planners face a similar dilemma. Their H-20 stealth bomber is still in development, with prototypes undergoing initial testing and no operational squadrons yet formed. China has devoted decades to refining defensive doctrines around anticipated American capabilities, but the B-21's operational pace undermines these preparations. By the time the H-20 becomes mission-ready, B-21 crews will have accumulated thousands of flight hours, integrated AI-assisted systems, and established operational concepts that effectively leapfrogged China's planned deployment schedule, forcing a fundamental recalibration of Chinese air defense planning. But here's the part most analysts miss. How one aircraft platform creates this kind of disruption reveals something far more significant than stealth technology alone. According to a leaked Air Force Global Strike Command memo, the B-21 Raider will fly 40-hour globe-spanning nuclear strike missions with just one human pilot on board. Not two pilots like every heavy bomber in American history. One pilot and one weapons systems officer. This single detail reveals the most significant shift in air warfare since stealth itself. Advanced AI autonomy has arrived in strategic aviation. Every current bomber requires multiple pilots because the cognitive load is immense. The B-52, B-1B Lancer, and even the B-2 Spirit operate with paired pilots and weapons officers. During marathon missions, they meticulously schedule every task, managing sleep in shifts to ensure alertness for weapons engagement and the complex, dangerous mid-flight refuelings that occur every few hours. Retired Air Force Colonel Mel Dell, who flew a record 44.3-hour B-2 mission, described the brutal reality, constantly reviewing target folders, monitoring fuel consumption, replanning routes when coordinates change mid-flight, which happens regularly, all while fighting fatigue so extreme that flight surgeons issue amphetamine, go pills just to keep pilots functional. The single pilot configuration reveals the B-21's true revolution. The pilot's role fundamentally shifts from actively flying the aircraft to supervising an artificial intelligence system that handles flight operations. But this isn't autopilot. Commercial autopilot executes pre-programmed directives. When circumstances change, humans must intervene manually. The B-21's AI operates on a completely different level. It processes data from the same sensor arrays human operators use, but responds faster and never experiences fatigue. When surface-to-air missile radar locks onto the bomber, the AI deploys radio frequency countermeasures and executes evasive maneuvers, potentially faster than human reaction time allows. When new battlefield threats emerge that weren't present during mission planning, the AI rapidly calculates optimal routes through contested airspace, automatically adjusting course while notifying the pilot. The AI handles routine operations and many complex tasks as effectively as human operators, allowing the pilot to serve primarily as mission supervisor. During extended missions, the human pilot can rest between refuelings while the AI manages flight operations. Strategic analysts understand what this means. America has operationally implemented jury AI-assisted combat aviation while adversaries are still building traditional crewed platforms. That is a generational technological leap that compounds over time as AI systems learn and improve. But even sophisticated AI can't help if enemy radar detects you. So how does a 40-meter wide aircraft achieve a radar cross-section the size of a tennis ball? Making a 40-meter wide aircraft appear the size of a tennis ball on radar screens isn't marketing exaggeration. It's the B-21's reported radar cross-section. And understanding why this matters requires grasping what stealth means in modern warfare. Every millimeter of this aircraft's surface matters. One imperfect seam, one slight edge, and stealth effectiveness degrades. Russian and Chinese air defense networks were designed to detect large metal structures with engines, wings, and distinct radar returns. The B-21 was engineered to betray none of those signatures. The bomber is covered in a specialized coating that absorbs radar waves rather than reflecting them. But this represents just the foundation of a multi-layered signature reduction system. The cockpit windows blend seamlessly into the airframe with minimal edges for radar to catch. Every joint, every seam, every crevice that could compromise the radar cross-section has been eliminated from external view. Onboard electronics don't just reduce radar signature, they can actively deceive enemy systems, making hostile radar see something that isn't there, or more accurately, see almost nothing worth investigating. The engines reveal engineering obsession. They're recessed deep into the wings, completely hidden from direct observation and angled to minimize thermal signatures. The narrow exhaust design represents a massive improvement over the B-2's configuration that created detectable heat signatures. The B-21's engines reach Mach 0.8, not supersonic, because when signature management is this effective, you don't need to outrun missiles. Speed creates noise and heat. Stealth creates operational advantage. Here's where physics becomes weaponized. Every curve on this aircraft is continuous. Every angle mirrors itself throughout the structure. When radar waves hit flat surfaces, they bounce directly back to the emitter, creating obvious radar returns. But curved surfaces scatter those waves in multiple directions simultaneously, fragmenting the radar return into background noise that operators dismiss as atmospheric interference. The construction process itself reveals the obsession. Unlike any aircraft in history, the B-21 is built from the outside in, completely backwards from normal assembly. Traditional aircraft are built from the inside out. Why reverse this proven method? Because radar detects surface imperfections, the smooth outer surface must be perfected before internal components are installed. On the B-2, maintenance crews had to hand-remove exterior coating to access wiring beneath over 100 panels, a process taking months in climate-controlled facilities. The B-21 has simple maintenance doors, allowing service work in normal hangars over hours. This seemingly minor detail has massive operational implications. You can actually use the bomber regularly instead of treating it like a museum piece. But signature reduction alone isn't what terrifies Russian strategists. What truly concerns them is how this platform adapts to threats that don't even exist yet. Every previous stealth bomber became outdated the moment it entered service. New threats emerged, technology advanced, and multi-billion-dollar aircraft became frozen in time. Upgrading meant years of retrofitting and astronomical costs. The B-21 shatters this paradigm with one revolutionary concept: open architecture software that turns a bomber into an infinitely adaptable weapons platform. Think of your smartphone. You don't buy a new device for different capabilities. You download apps. The B-21 applies this exact logic to weapon systems and mission profiles. Need to share real-time location data with satellites? Software integration? Want to run a new electronic warfare program? Download and deploy it. The bomber can be reconfigured for entirely different missions between sorties. Engineers can develop specialized reconnaissance systems, test them, deploy them on a mission, then seamlessly replace them with combat-focused configurations the next day. No hardware replacement required, no months of retrofitting, pure adaptability. This represents warfare reimagined. Russian military planners build defenses against known capabilities, specific sensors, particular weapon systems, and understood tactics. But how do you defend against a platform that fundamentally changes what it can do between missions? Today's reconnaissance aircraft becomes tomorrow's electronic warfare platform, which becomes next week's drone command center, all using the same airframe. The B-21 was designed as one component in a family of systems, integrating with joint all-domain command and control, connecting every sensor across the U.S. military for instant information sharing. Satellites, drones, submarines, tanks, ships, and bombers share information simultaneously, functioning like interconnected nodes of a single distributed intelligence, spanning all domains. Future operational concepts envision the B-21 flying alongside autonomous drone wingmen that guide, share targeting data, and act as decoys to distract enemy radar. But the bomber isn't just dropping ordnance. It serves as an airborne command center, issuing real-time orders to drones, directing formations, coordinating with naval assets, all while maintaining its primary strike capability. Consider the scenario keeping Chinese military planners awake. China begins operations against Taiwan. Within minutes, a B-21 launches from a Pacific base. It arrives coordinating drone swarms, accessing communication networks to locate high-value targets, directing precision strikes without ever entering hostile airspace itself. The bomber carries long-range weapons with standoff capability and an 11,000-kilometer unrefueled range. Virtually no location on Earth remains beyond reach. Here's what truly matters. The brilliance isn't being the newest technology. It's perpetually adapting to what's new. Open architecture means continuous capability enhancement. Revolutionary sensors developed in 5 years? Integrate them seamlessly. Next-generation electronic warfare capabilities? Download and deploy. Advanced AI algorithms? Update the software. Whatever technological breakthroughs emerge over the next 3 decades, This platform absorbs them without requiring new aircraft. Russia's PAKDA and China's H-20 are being designed for today's battlefield using today's technology. The B-21 is being designed for battlefields that haven't been imagined yet, but software means nothing if you can't manufacture the actual aircraft at scale. And here's where the production numbers should genuinely concern adversaries. Welcome to Plant 42, Northrop Grumman's partially classified facility in Palmdale, California, where 8,000 workers are manufacturing America's stealth bomber fleet at a pace that fundamentally changes strategic calculations. Current intelligence suggests they're delivering 7 to 8 aircraft annually, and that production tempo is accelerating. To understand why this matters, consider the catastrophic B-2 procurement failure. Original plans called for 132 aircraft at $500 million each. What did America actually receive? 21 planes costing $2 billion apiece. The Cold War's end triggered military budget cuts, and the most advanced bomber fleet in history died stillborn. Too few aircraft, too expensive to operate, too maintenance-intensive to deploy regularly. The Air Force explicitly demanded cost discipline for B-21 development. Each aircraft costs approximately $700 million. Classified items mean actual costs run higher, but nowhere near B-2 levels. More critically, this bomber services in standard hangars for hours instead of months, enabling sustained operations rather than occasional symbolic missions. The manufacturing revolution enabling this pace is driven by augmented reality and digital twin technology. Engineers don't just build physical aircraft. They work with perfect digital replicas, testing newly developed systems in virtual environments before anything reaches the production line. Design flaws discovered in digital twins get fixed with software changes rather than million-dollar physical retrofits. This digital thread shares across all of Northrop's partners as they develop complementary systems, ensuring seamless integration before the first component is manufactured. Want to test a radical new sensor configuration? Run it in simulation. Does it work? Build it. Does it fail? Delete it and iterate. Zero wasted materials, minimal risk. The strategic implications are profound. Russia and China are developing stealth bombers, singular experimental platforms that might enter limited service in the 2030s if development proceeds perfectly. America is manufacturing B-21s at scale right now, building institutional knowledge, refining production processes, and preparing operational squadrons while adversaries are still testing prototypes. 3 B-21s currently exist. By the time Russia's PAKDA or China's H-20 reach initial operational capability, dozens more Raiders will be operational with crews who've accumulated thousands of flight hours. By the time those foreign platforms achieve full operational status, American squadrons will have refined tactics, integrated new capabilities through software updates, and developed operational concepts adversaries won't understand until experiencing them in conflict. The planned fleet of 100 Raiders will retire 45 B-1Bs and 20 B-2s, potentially even phasing out the B-52 that's been flying for over 70 years. It is a complete reconceptualization of strategic bombing built around sustained operations rather than occasional deployment of precious, irreplaceable assets. Every aircraft rolling out of Plant 42 represents a node in a networked warfare ecosystem. Each can share data with every platform, coordinate with autonomous drones, and update software to match evolving threats. Russia isn't facing one new bomber. They're facing a self-improving fleet that becomes more capable with every software update, every sensor integration, every tactical lesson learned. So we have a low observable bomber with AI-assisted operations that adapts to future threats and is being mass-produced right now. But what does this actually mean when tensions escalate? The B-21 Raider has exactly one mission, stated with brutal clarity: prevail in great power conflict against Russia or China. Not counter-terrorism, not regional operations. Total war against near-peer adversaries with sophisticated air defenses, advanced fighters, and their own stealth programs. Strategic analysts understand this aircraft represents something beyond incremental advancement. It's a platform that fundamentally alters how great powers calculate risk. Strategic bombing evolved over a century from German Zeppelins over London in World War I to America's current fleet. The B-52 Stratofortress, with its massive 70,000-pound payload, the supersonic B-1B Lancer using speed to evade defenses, and the B-2 Spirit designed to penetrate hostile airspace through stealth. All three were designed for different eras with different assumptions. The B-21 was designed for an integrated battle space where cyber warfare, electronic attacks, hypersonic missiles, and autonomous drone swarms converged simultaneously. A battlefield that barely existed when those older aircraft entered service. The flying wing design maximizes lift while minimizing drag, requiring less power and extending both range and loiter time. With an 11,000-kilometer range without refueling, there's literally nowhere on Earth beyond reach. Combine that range with long-range weapons, and the bomber doesn't need proximity to targets. The psychological calculus shifts entirely. Adversaries cannot reliably track where the B-21 is, cannot track it when nearby, and face severe challenges preventing mission completion. Now layer in the capabilities already discussed, and the platform's true purpose becomes clear. The AI co-pilot enables sustained 40-hour missions with a single human on board, not by reducing workload, but by absorbing entire categories of decision-making, navigation, threat avoidance, sensor fusion, and real-time route optimization, allowing the pilot to function as a mission commander rather than an operator. Open architecture software means the aircraft is never locked into a single role. Mission packages can be rewritten between sorties, transforming the bomber from a strike platform into an intelligence node, an electronic warfare asset, or a command relay without structural modification. Integrated with satellite networks and autonomous drone wingmen, the B-21 operates as the airborne nerve center of a distributed force, directing unmanned systems, sharing targeting data across domains, and shaping the battle space before weapons are released. Its electronic warfare suite does not simply evade defenses, it actively degrades, misleads, and fragments adversary sensor networks, collapsing their ability to see the fight as a coherent whole. If conflict erupts, the B-21 leads without being near the fight. It coordinates drone swarms, directs naval assets, shares targeting data with ground forces, all while maintaining the option to engage targets from standoff ranges. Joint all-domain command and control means information flows instantaneously. What one sensor detects, every platform knows simultaneously. Consider force structure implications. 100 B-21 Raiders, replacing 45 B-1Bs, 20 B-2s, and potentially the entire B-52 fleet. Some might consider it a replacement, but it's a reconceptualization of strategic bombing doctrine. Older platforms could barely afford to fly due to operational costs. The B-21 is designed for regular, sustained operations, making deterrence credible rather than theoretical. Russia's PAKDA and China's H-20 are responses to American air dominance, attempts to match capabilities that debuted decades ago with the B-2. But they're building bombers while America built a warfare ecosystem. Even if adversaries successfully field stealth platforms, they're entering a game where the rules fundamentally changed. The geopolitical message is unmistakable. America remains multiple generations ahead in strategic warfare technology. While adversaries struggle to field experimental prototypes, the U.S. manufactures at scale, refines operational concepts, and prepares for conflicts that haven't been conceived yet. 3 B-21 Raiders exist today. Production accelerates. By the time foreign programs reach operational status, American crews will have accumulated experience that adversaries won't match for years. And the real test of the B-21 won't be when it flies, but when adversaries realize they can't reliably defend against it. Since the unveiling of the White Emperor, comparisons to the U.S.'s NGAD and F-22 have sparked intense debate. Analysts are scrutinizing every detail, from speed and stealth to firepower, as the battle lines in the race for air dominance are clearly drawn. How does the White Emperor truly measure up against these American fighters? And could it tip the balance of power in the skies for years to come? Join us as we compare the capabilities of two sixth-generation air fighters that are bound to change the future of aerial warfare. As tensions between Washington and Beijing continue to escalate, The global race to field sixth-generation fighter aircraft has reached a critical stage, with both nations pouring immense resources into developing platforms designed to dominate the skies and achieve strategic air superiority. The U.S. Air Force's Next Generation Air Dominance Program, or NGAD, is projected to set a new standard when it enters service over the next decade, boasting a combination of manned and unmanned systems, cutting-edge stealth, advanced adaptive engines, and integrated sensor networks. On the other hand, the People's Liberation Army Air Force is constructing its own next-generation fighter, dubbed the White Emperor, which was unveiled recently at the Zhuhai Air Show. According to state-run reports, this ambitious platform is intended to operate not only in the atmosphere, but potentially in near space, showing China's push for strategic flexibility and technological prestige. While some of these claims may appear exaggerated, the rapid pace of Beijing's military modernization, combined with its expanding aerospace capabilities, makes the program a serious point of concern for U.S. military planners. Publicly available images and video footage reveal a fighter with large internal missile bays, capable of carrying increased ordnance without compromising stealth, and a delta-shaped aerodynamic design that emphasizes both speed and maneuverability. Analysts, including the Bulgarian military, have noted the platform's carefully engineered pointed nose, smooth body contours, and multi-layered cockpit canopy, all optimized to reduce radar and infrared signatures, signaling the PLAAF's focus on next-generation stealth. The aircraft's design is said to emphasize a low observable profile while maximizing high-speed maneuverability, allowing it to survive and dominate in contested airspace against advanced fifth-generation and future sixth-generation adversaries. Central to its agility are advanced thrust vectoring engines and a restructured fuselage, which theoretically grant the fighter super maneuverability similar to what the F-22 Raptor can achieve. Such extreme directional responsiveness would be essential in high-stakes air-to-air engagements, enabling pilots to evade missiles, counter hostile fighters, and execute precision strikes under conditions where split-second reaction times could determine the outcome of a battle. The fighter is also reportedly designed with an expanded internal weapons bay, capable of carrying a variety of munitions for multiple mission profiles. This flexibility would allow a single aircraft to switch seamlessly between air-to-air combat, air-to-ground strikes, and even near-space operations, giving the People's Liberation Army Air Force a highly adaptable and survivable tool for both traditional and emerging battle domains. Further distinguishing the White Emperor from its predecessors is the inclusion of directed energy weapons, most notably lasers. These systems, integrated into the airframe, are likely intended to provide simultaneous multi-target engagement, allowing the aircraft to neutralize multiple threats in rapid succession. This capability exemplifies next-generation combat thinking, where advanced sensors, stealth, and precision energy weapons work in concert to provide a decisive advantage. According to reports, including analysis from China Arms, test flights of the White Emperor suggest that the platform is not merely theoretical. It has demonstrated the potential to operate across multiple domains. The aircraft is envisioned to engage in air-to-air duels, precision strikes against ground targets, and missions in near-space environments, where conventional fighters cannot operate effectively. The aerodynamic design also plays a critical role in the fighter's performance. Sleek aerodynamic lines reduce drag while improving stealth, and the multi-layered, reflective minimizing cockpit canopy likely shields pilots from detection. Delta-shaped wings and advanced control surfaces further enhance speed, stability, and responsiveness at supersonic velocities, making the aircraft difficult to track, target, or intercept. Internally, avionics, sensors, and weapon systems are integrated into a unified network, allowing real-time data fusion and rapid decision-making during complex missions. This convergence of stealth, propulsion, and energy weapons is intended to produce a fighter capable of operating independently or in concert with unmanned systems, providing both redundancy and force multiplication. Artificial intelligence plays a central role in the White Emperor, elevating it beyond the capabilities of even the most advanced fifth-generation fighters. This next-generation system is said to process vast streams of real-time data, assess incoming threats, and execute tactical maneuvers without requiring constant pilot input. Such an approach opens the door for both semi-autonomous and fully autonomous missions, where the human role could shift from direct control to mission supervision. This is not just theory. A similar capability has already been demonstrated by the United States Air Force with the experimental X-62 Vista, which showcased how artificial intelligence could assume control of a combat jet in live environments. By following this model, the White Emperor may mark the point where autonomy moves from experimental programs into operational fighter platforms. For the pilot, the benefit is transformative. Instead of being overwhelmed with multiple information streams in the chaos of aerial combat, the onboard systems powered by artificial intelligence deliver immediate, actionable intelligence. Threats can be detected, analyzed, and prioritized in fractions of a second, allowing the pilot to respond faster than human reflexes alone would ever permit. In this sense, the human operator becomes the mission director, relying on the jet's artificial intelligence to execute rapid maneuvers, select optimal weapons, and even coordinate with allied aircraft or unmanned systems flying alongside. Such AI-driven situational awareness effectively allows the White Emperor to fight as a central node in a vast digital battle network. The Aviation Industry Corporation of China has clearly positioned this technology not as an optional feature, but as a core design philosophy. The Indian Defense Research Wing underscored this shift, noting that AVIC's design prioritizes artificial intelligence not just for tactical maneuvering, but as an integral component of multi-unit, networked combat. In practice, this means the White Emperor could seamlessly integrate with other fighters, drones, or command and control systems, exchanging data in real time and executing coordinated strikes across multiple domains. It is a concept that mirrors and perhaps seeks to outpace the United States Air Force's vision for its own next-generation air dominance program, where manned and unmanned systems are designed to operate as a single cohesive force. By integrating this level of autonomy, China is signaling its intent to compete not only in the development of stealth, propulsion, and weapons technologies, but also in the field of digital warfare. The White Emperor could potentially reduce the need for continuous human oversight in high-risk missions, sending unmanned or semi-autonomous units deep into contested airspace where survival odds for a pilot would be minimal. This possibility represents both a technological leap and a strategic shift, moving warfare into an era where decisions are increasingly made by machine intelligence guided by human objectives. The White Emperor is built to be far more than a single-purpose aircraft. Its designers envisioned a machine capable of adapting to nearly any role on the battlefield. This fighter is intended for multi-role missions, able to take on air-to-air engagements, air-to-ground strikes, and even operations in what China claims are near-space environments. Embracing this range, it attempts to cover multiple mission types with one highly adaptable platform. Such flexibility reflects China's broader ambition to field aircraft that are not only powerful but also versatile enough to meet unpredictable combat demands. A major reason for this adaptability lies in the White Emperor's modular systems. Unlike older aircraft that require significant modifications for new missions, the White Emperor can be configured quickly for different combat scenarios. This means the jet can transition from conducting deep strike missions to performing air superiority patrols with minimal delay. In practical terms, this versatility allows China's Air Force to deploy fewer aircraft while still maintaining coverage across a wide variety of missions. By reducing logistical strain and increasing readiness, the White Emperor strengthens China's ability to conduct long, sustained campaigns without exhausting its resources. Equally important is the emphasis on maintenance. A VIC designed for White Emperor with low maintenance requirements in mind. Traditional fourth-generation jets often suffer from long downtimes after missions, but the White Emperor promises high availability with minimal turnaround time. For prolonged operations, where every minute matters, this capability ensures the aircraft can stay in the fight longer and return to the skies faster. It is not just about performance during combat, but also about endurance over the course of days, weeks, or even months of deployment. Where the White Emperor truly shows its futuristic intent is in its networked warfare capabilities. The jet is not meant to fight alone. Instead, it is designed to integrate seamlessly into China's future combat networks, linking up with other aircraft, ground units, and even naval forces. Such interconnectivity transforms the jet from a single war machine into a node in a vast, coordinated system. This concept mirrors the approach of Western programs, such as the United States Air Force's collaborative combat aircraft initiatives, where drones and manned jets work in harmony. By being able to communicate in real time, the aircraft expands tactical options on the battlefield. Pilots can receive live data from drones, pass targeting information to ships, or coordinate with ground-based missile systems. The effect is a wider, more unified battlefield picture, enabling swifter decision-making and more precise strikes. The South China Morning Post emphasized this point by noting, "The jet's networked capability allows coordinated actions with diverse units, reinforcing China's bid for air superiority." Artificial intelligence plays a central role in this networked vision. The White Emperor's onboard systems are designed to process massive amounts of data in real time, filtering and prioritizing information for the pilot, or even handling coordination autonomously. When combined with drones and ground units, this creates a combat environment where China's forces can act faster than their opponents, tightening the decision loop in their favor. Taken together, the White Emperor's operational flexibility and networked capabilities highlight China's determination to dominate future battlefields. By merging adaptability, endurance, and interconnectivity, the aircraft is presented as a cornerstone of a larger vision, one where Chinese forces can seamlessly coordinate across air, land, and sea, maintaining the upper hand in complex, high-intensity conflicts. Unlike traditional fighters, the White Emperor is often described as more than an aircraft, standing somewhere between a combat jet and an aerospace vehicle. Its rumored ability to operate at near-space altitudes marks a fundamental shift in how air dominance might be defined in the future. Reports have emphasized that China's defense industry wants to achieve a qualitative leap that challenges existing superiority dynamics. According to the National Interest, the White Emperor series could reshape contested airspace by bolstering China's ability to project power far beyond its borders. If realized, such an aircraft would not merely match foreign developments, but could redefine them, forcing adversaries to prepare for combat environments extending into the stratosphere. Although details remain scarce, particularly in English-language sources, speculation paints a picture of extraordinary performance. The White Emperor is believed to be capable of reaching top speeds near Mach 5, translating to almost 6,000 kilometers per hour and covering operational ranges beyond 4,500 miles. Its ceiling is claimed to extend past 100,000 feet, placing it within near-space territory where traditional air defenses lose much of their effectiveness. These numbers alone, if proven accurate, would mark the White Emperor as a once-in-a-generation leap in aerial engineering, setting it apart not only from fifth-generation fighters like the F-35 or the J-20, but also from projects aimed at the sixth generation. The role of artificial intelligence is perhaps the most revolutionary aspect. Instead of simply assisting the pilot with navigation or weapons targeting, the White Emperor is expected to function with full autonomy when required. Real-time decision-making, data assessment, and threat prioritization could all be handled by onboard algorithms, giving the jet an option to operate as an unmanned system. Such autonomy would not only reduce risk to human pilots, but also allow the aircraft to push beyond human physiological limits, especially in high-speed, high-altitude engagements. In parallel, its weapon loadout, which is rumored to include hypersonic missiles and directed energy lasers, would give it the capability to strike with both overwhelming force and precision. Another significant factor is the promise of minimal maintenance requirements. If China's designers succeed in reducing logistical burdens, the White Emperor would not only be more powerful than many of its rivals, but also more available, spending less time grounded and more time deployed on missions. This would give the PLAAF a considerable operational advantage in a drawn-out conflict, where rapid redeployment and sustained pressure are key. Much like the NGAD fighter, the White Emperor is expected to operate alongside unmanned systems, with loyal wingman drones serving as expendable extensions of the manned aircraft's operational reach. In the NGAD framework, Collective Combat Aircraft, or CCA drones, accompany the main fighter, reducing the need for larger quantities of manned aircraft and lowering program costs while providing unprecedented battlefield flexibility. The projected timeline for China's sixth-generation fighter calls for operational deployment by 2035, which means a functional design must emerge before the end of this decade, placing significant pressure on designers and engineers. The United States, however, appears further along in the program, integrating advanced adaptive engines, AESA radars, and networked sensor fusion to create a versatile and stealthy aerial platform capable of dominating contested airspace. On the 21st of March, 2025, President Trump announced that Boeing had been selected to build the United States Air Force's sixth-generation fighter to meet the NGAD requirement, revealing that the aircraft would be known as the F-47. The previous year had seen dramatic shifts in America's two next-generation air dominance programs. Budget pressures forced a re-evaluation of priorities, pausing the source selection process for NGAD. The Air Force was instructed to reconsider not only the capabilities it required from the crewed fighter at the heart of the NGAD system, but also whether such an aircraft remained necessary at all. Simultaneously, the United States Navy's F/A-XX effort, often also called NGAD, received renewed attention, clarifying earlier misconceptions that the program had been halted entirely. New strategic challenges quickly emerged. Potential adversaries, particularly China, sought ways to deny the U.S. and its allies the freedom to conduct operations in their preferred manner. China's response took the form of the Anti-Access Area Denial Strategy, or A2/AD, designed to prevent American forces from entering key operational areas and to limit their freedom of action within those zones. By using long-range air defenses, advanced missiles, hypersonic glide vehicles, and layered detection systems, China aims to push enemy aircraft to more distant bases, complicate refueling and battle management, and disrupt operational tempo. It is important to note that A2/AD does not make airspace impenetrable. Instead, it forces adversaries to operate under constraints, slowing or redirecting their actions and preventing deep strikes. In parallel, China has sought to achieve significant mass in its forces, challenging the numerical advantage the United States once enjoyed. Andrew Hunter, the outgoing acquisition executive for the U.S. Air Force, acknowledged the competitive pressures, noting that China could beat the U.S. to the punch. He added that while the U.S. may eventually possess superior capability, the U.S. certainly has no time to lose. Current American fighters, such as the F-35A, have a combat radius of only 590 nautical miles, or 1,093 kilometers, while the F-22A has an even smaller radius when relying on supercruise. Both aircraft would need to refuel within approximately 500 nautical miles, or 926 kilometers, of their targets, a requirement that places tankers in vulnerable positions, effectively leaving them as sitting ducks under modern A2/AD conditions. This evolving environment demonstrates why NGAD, combined with advanced air refueling and networked operations, is critical. Without such innovations, U.S. and allied air forces would struggle to penetrate adversary defenses, sustain prolonged missions, or maintain the operational freedom necessary to secure decisive air superiority in the decades ahead. The strategic and technological imperatives driving NGAD reflect a profound shift in how aerial warfare will be conducted against peer adversaries. Another uncomfortable reality is that the United States Air Force can barely afford a next-generation air dominance fighter with a unit cost of approximately $300 million within the time frame the aircraft will be required. This is unusual for a service that has historically been the best-funded Air Force in the world. Currently, the U.S. Air Force is prioritizing the two legs of the nuclear triad for which it is responsible, the B-21 A-Raider bomber and the LGM-35A Sentinel, also known as the ground-based strategic deterrent. Both programs consume a massive portion of the budget, and with the Sentinel program's cost nearly doubling to just under $141 billion, there is little room left for an expensive NGAD manned fighter. This budget constraint, rather than any change in threat perception, drives the push to reduce NGAD costs. Ultimately, a high-capability, long-range NGAD Corps manned fighter is essential, even if it comes at a high cost. Only about 200 units are expected, and none will likely be exported, limiting economies of scale. Proposals for lighter NGAD variants would augment, rather than replace, the main platform. The Air Force has long considered dual versions, one optimized for long-range, heavy payloads in the Indo-Pacific, and another for shorter-range operations in Europe. The vision includes a clean-sheet design with open mission systems capable of rapid software updates, ensuring the NGAD remains a high-end fighter while allowing smaller, lower-cost aircraft to handle day-to-day missions, preserving the core platform for high-intensity operations. Thanks for watching. Before you go, click the link on your screen to check out another video. See you there.